Hello, honors physics students. Okay, so we're looking here at our last question on the concepts page number 12, where we had taken these row of positive point charges and the row of negative point charges. We built up the field between them, and then we extended to the idea of what if it's not individual point charges? What if it's a big metal plate just covered in positive charge? Instead of these negative point charges, it's a big metal plate covered in negative charges. What happens is the field lines all straighten out. There's no more curvature to them, and they're also evenly spaced, which, based on Rule 5, tells us that since the field lines are not bunched together anywhere or spread apart anywhere, they have the same density everywhere, they have the same strength everywhere. And is the only way to get the uniform electric field, these oppositely charged parallel plates. An incredibly useful method of simplifying problems here. We don't have to worry about the strength of the field. Everywhere we look, the field will be the exact same everywhere, anywhere in between the plates, even right up against the plates. All right, so what can we do this? Well, we keep going back to comparing electric effects to gravitational effects, and even though we certainly established they're not the same thing, and there are enough dissimilarities that we can't even say they're close in terms of magnitudes, in terms of strengths, there's still enough similarities that we can use what we know about gravity to help inform us about electric fields, okay? So let's do a side-by-side comparison of a uniform gravitational field versus a uniform electric field. All right, so the first question is, well, how do we get a uniform gravitational field? So I want you to just pause the video and think about that for a little bit. What arrangement of masses would produce a uniform gravitational field? Okay, so hopefully you came up with some ideas, although, it's a bit of an abstract concept here. Well, one of the things I want to remind you of, what's the symbol for gravitational field? Hopefully, of course, remember that's lowercase g. If instead you said it was F sub g, you're still confused between force and field, and that's something we've been battling since we first introduced the idea that you really have to know the difference between them, that force numbers an interaction between objects, field is a single object's influence on the space around it, right? So lowercase g is our symbol for gravitational field, and then hopefully remember what's the other meaning for lowercase g. Well, hopefully remember that's acceleration due to gravity. And once again, if instead you said it's force of gravity, you're really confused, and you must go back and review the difference between force and field. Lowercase g is acceleration due to gravity, which is also gravitational field. Okay, so then in class I would say, well, what's the strength of Earth's gravitational field right here in class? Well, since we just reminded ourselves it's acceleration due to gravity, hopefully you would say it's 9.8 meters per second squared. And where I'm sitting right here, the value of g is 9.8 meters per second squared. And where you're sitting there at home, the value of g is 9.8 meters per second squared. In other words, pretty much everywhere on Earth, we're sitting in a uniform gravitational field, as long as we're close enough to Earth. If we're close enough to Earth, Earth is flat. We know, of course, Earth is not flat, but the point is that there's not enough change in it, and so when we draw its field, all the field lines are pointing straight down. They're evenly spaced because everywhere we look along what we're presuming is a flat Earth, or locally is flat, the value of g is always 9.8 meters per second squared. It's only when you get far enough away that you can see the changing, the spreading apart of the field lines, and the weakening of Earth's gravitational field when you can see the curvature of Earth. And of course we explored that in previous topics. Alright, so let's imagine we take an object of mass m, and we're going to lift it against Earth's gravitational field at this angle here, going through some displacement, delta x, raise some height change, delta h, away from Earth's surface, away from 0. And let's say we're going to do this at a constant velocity. Now, as soon as I say constant velocity, all sorts of things should pop into your head, right? In fact, maybe write down a couple of things you know if an object is moving at constant velocity. Right? So we know it's in equilibrium. We know that the acceleration is 0, net force is 0, right? Constant velocity, no change in velocity. All right, so next what we'll do is we'll draw a free body diagram. It's been a while since we've done a full free body diagram, so of course what force do we start with? Right, of course, force of gravity pointing which way? Straight down. So here's mg, and we're going to write it as F sub g equals mg. I want you to write it this way. You'll see why soon. And of course, we're lifting it, which means we're applying a force upwards. And since we just established it's going at a constant velocity, the net force is 0, we know that our force upwards is going to exactly counteract the force of gravity downwards. And so our force in magnitude is also equal to mg. Right? We're just maintaining its motion. We're not speeding up or slowing down or changing direction. Our force exactly counteracts the force of gravity. It's already in motion. Well, we're applying a force through a displacement, which means we're doing some work, right? So what's the equation for work? Well, the most generic equation is F delta x cosine theta. So here we're reviewing forces, reviewing free body diagrams. Now we're going to review work a little bit. Okay, so F delta x cosine theta, the force we're using in magnitude is equal to mg. We're moving through displacement delta x. Ooh, but what about theta? Let's remind ourselves, where is theta measured when we do F delta x cosine theta? Okay, right, it's always between the two previous vectors. Anytime the angle theta is part of the equation, always refers back to the two previous vectors, so it's the angle between the force you're using and the delta x. So here's theta right in there. And now we get to play one of our favorite games. That's right, find theta. Okay, so let's look at this big triangle, this geometric triangle. Here's the hypotenuse of a triangle, delta x. Here's this side, delta H, and here's the other side. Let's see if we can get theta into this big triangle. I want you to just pause the video for a second, see if you can get theta into this big triangle here. Alright, so hopefully you see by alternate interior angles, there's the z, that theta ends up over here, and it's not even theta we need, it's actually cosine theta. So looking at this triangle, what is cosine theta equal to? Go ahead and pause the video and write down what you think cosine theta is in relation to this big triangle. Of course, it's going to be adjacent over hypotenuse. That's going to be delta H, adjacent over hypotenuse delta X, looking at the geometric dimensions of this triangle. So here's cosine theta, which we put in here. So it's mg delta X times delta H over delta X. And already you should see the delta X's will cancel, no problem there. We're left with the work that you're doing in lifting at constant velocity is mg delta H. Well, this looks awfully familiar. What's mg delta H? Hopefully you said change in potential energy, right? Not just potential energy, there's a delta H here, so it's a change in potential energy. And you must know the difference between the quantity and the change in the quantity. The quantity itself is just mgh. So remember, this is how we actually derive the equation for gravitational potential energy as mgh. A change in it, though, would be a change in height. Okay? Alright, so that was a great review. Free body diagrams, forces, acceleration, work, fantastic. Okay, and this is all based on a uniform gravitational field. Now, next to this, let's draw a uniform electric field, which we already know the only way to get that is the oppositely charged parallel plates. So here they are. We're just going to recreate the exact picture we had there back in concept question number 12. The field lines are pointing from positive to negative, evenly spaced, all parallel to each other. Let's take a positive charge. I'm going to call it lowercase q because it's not the one creating the field. The plates are creating the field. It's like the test charge, and we're going to move it against the field, again, an angle here, a displacement delta x, moving it through a change of position delta d away from the negative plate. So you can see I'm clearly doing a side-by-side comparison here, basically doing the same idea, and let's say we're going to move it at constant velocity. So we know the acceleration is 0, the net force is 0, and we're applying a force to it, but of course that force is counteracted by the electrostatic force, right? If we were to just let this go, we would follow the field lines by rule number 1, feeling a force in the same direction as the field, given by q times z. Now let's just pause here for a second and reflect, why are we not using Coulomb's law? Why are we not using k big Q little q over r squared? Well, you recall that equation is only for point charges, plural, point charges. And while this here, lowercase q, is a point charge, the plates, the other charged objects, are clearly not point charges. And that's something you really have to make sure you're very clear about. You can only use Coulomb's law if both the objects in the direction are point charges. Any other geometry, and you can't use it. Plus, we don't even have the charge on it anyway, but the point is that certainly this will feel a force because of the field created by the oppositely charged parallel plates. Now we're moving constant velocity, which means we're applying a force in the opposite direction, which we know is going to be equal in magnitude to q times z because the net force is going to be 0. So here's our force. We're applying a force through displacement. We're going to be doing some work. F delta x cosine theta. In this case, the force in magnitude is going to be q times z. What about theta? Well, just like before, theta is going to be between the force you're using and the displacement. And I'm going through this a little more quickly because you should see here it's the exact same thing as before. What's cosine theta here? Well, theta we get into the triangle by doing alternate interior angles. Here we have adjacent, here we have hypotenuse, here cosine theta is delta d over delta x. Put that in, QE delta x times delta d over delta x. The delta x's cancel. We're left with QE delta d, which clearly is an analog to mg delta h. Which means that if we're doing some work, we're pushing this positive charge closer and closer to the positive plates and putting it in a position where it doesn't want to be. What does that sound like? That sounds like potential energy. This must be a new form of potential energy here based on QED, just like this is MGH. And notice that I'm making all these analogs, which is why I want you to keep writing F sub E as Q times E, because this says force equals object times field, just like this here says force equals object times field. This potential energy is object, field, position. This potential energy is object, field, position. I'm really trying to make this side-by-side comparison so you can see all the stuff we've done before in gravity as a complete analog here in electrostatic effects. Now we do have to add in a subscript. Here we add a subscript lowercase g for gravitational potential energy. We use subscript s for spring potential energy. What's the subscript here? Well, it's got to be an E. Alright, so you only get one chance to laugh at this. I'm not here even there. If you want to pause the video and laugh a little bit more about this, that's fine, but that's going to be our symbol for electric potential energy. We're going to go ahead and box it in as our new equation. Let's define our terms. So PE sub E is electric potential energy, and it's energy, so of course we know it's going to be scalar, and units are going to be joules. You can prove it to yourself if you'd like to, but all forms of energy, of course, are scalar. All forms of energy are joules. Alright, what about the other terms? The lowercase q, Well, we've been using it as the test charge. We're just going to rename this as the moving charge, because we are now moving it around inside someone else's field. And we also want to be very clear that while it does create its own field, that's not this field here. It's the one not creating the field. We always have to be very careful. What's creating the field? What's experiencing the field? E is the field created by something else, so we call it an external and a uniform electric field. In this case, it's produced by the plates. Remember, this equation will only work for a uniform field. That's the whole way we started this. And what about D? Well, D is clearly playing the role of H, but why am I not calling it H? Let's explore that for a little bit. Here, this is H because we're moving it against the gravitational field, and H is always measured from bottom to top, right? You always measure height from bottom to top. We never measure H the opposite way, and yet, while D is playing the same role, I'm not calling it H, and here's why. So here we just took all that stuff away. Let's say we're taking this positive charge, and we're moving it this way, clearly increasing its height. But what if we're not moving it that way? What if we're moving the other way to increase potential energy? Well, that doesn't make any sense, right? Because it's only going to increase in potential energy when it's going closer where it doesn't want to be. But see, the plates don't have to be arranged this way. What if I flip the plates? So now positive is here, negative is here, and the field's pointing the other way. Which way would I be moving the charge to increase its potential energy? That would be moving down, right? Towards the positive plate. That's where it doesn't want to be. That's where it has more potential energy, and clearly it's not moving up, so we can't call that an increase in height. That's just something else. Height is never measured down, right? What if we arrange the plates this way? No one says they have to be arranged top-bottom. We're going to arrange side by side. Now, if I move this positive charge where it has more potential energy closer to the positive plate, well, that's not a change in height at all. And so we can't use H here because it's not necessarily a change in height. It's not always an increase in height. And so instead, we're going to call it D as the distance away from wherever the electric potential energy equals 0. Which, if you think about it, is sort of the same thing as height, right? Height is measured from bottom to top. It has the lowest potential energy down here. When you increase its height, you're moving it away from where it has 0 potential energy. So that's the same idea. So we're going to call this D the position or distance away from wherever it has 0 potential energy. Notice I'm also using absolute value of Q. Now that's rather important. This way we can define D regardless of, what the charge is, based on what sort of sign the charge has, but we're still going to get the same answers here because we're going to eliminate the sign on it. So let's, again, remove all these parts here. Where would D be equal to 0? In other words, where would this positive charge have 0 potential energy? Where does it want it to be? Well, it wants to be at the negative plate. So in this case, we call D equals 0 here at the negative plate. You can remember, just like with height, you can call the 0 wherever you want, wherever it makes the most sense in the problem. And this positive charge wants to be at the negative plate. So we'll call that D equals 0. We'll measure D away from that negative plate. But again, here's another reason why it's not the same thing as height, because what if it's not a positive charge? What if it is a negative charge? Where does this charge want to be? Well, it's going to want to be at the positive plate, right? And so it wants to be at the positive plate. We're going to call D equals 0 there. We measure D away from the positive, and that will give it potential energy. And then you don't have to worry about the sign. Another good reason why we disregard the sign here. Now, the book's going to have a different equation for this. I think it's a lot more complicated. So I strongly advise you not to use the book's version and use this version the way we define D and using absolute value. All right, one last thing about this equation, again, is that it will only work for uniform fields. That's how we started this whole thing, right? Just like this equation, MGH actually only works if G is constant. If you were to try to do this when G gets much smaller, as we get much farther away from Earth, this equation is not actually valid. And so this equation will only work for oppositely charged parallel plates where there's a uniform field. You have to describe another equation if the field is changing. Okay, so that was a great review. We had forces, we had free body diagrams, we had acceleration, we had work, we had energy. But wait a second, now that we have a new sort of potential energy, that should remind you of something. We know something about forces that have potential energies associated with them. We have gravitational potential energy, we have spring potential energy. So you might remember something about the gravitational force and the spring force. They fall into a certain category. You recall? Conservative. Right, so now we have our third conservative force. Any force associated with potential energy is a conservative force. What does that mean? Well, you recall our big idea, as I call it the physics pickup line for picking up people at your physics parties, that work done by it or against it is path independent. It doesn't matter how the object gets from here to there inside the field. The work done by the electric field or work done against the electric field is path independent. You'll do the same amount of work and get the same results either way. And so now all the stuff with energy is coming back with conservation of energy. You can write conservation of energy equations involving the electric potential energy. You might also recall a little equation about the work done by conservative forces. It always serves to decrease the electric potential energy, where W sub E is the work done by the electric field. If you are looking at the work done by the field, it's always going to try to decrease the object's potential energy. All objects want to lose potential energy as they're let go to do what they want to do. They go where they want to go. They lose potential energy.